In the last section, we talked about the first derivative and graphs, and in this section, well, we're going to talk about the second derivative and graphs. So first, we should start by talking about what the second derivative is. F double prime of x, d squared y over dx squared, and y double prime all represent the second derivative of y equals f of x. So the second derivative is really just the derivative of the derivative. So if I was working with a function, let's say y equals 3x to the fourth minus 8x squared plus 9x, let's say. The first derivative, y prime, would be 12x to the third minus 16x plus 9. So there we just used the power rule just like we normally would. For y double prime, the second derivative, I would just take the derivative of my derivative. I would just take the derivative again. So I would end up with 36x squared minus 16, derivative of 9 is 0, and hey, there we go. So we just take the derivative 2 times if we wanted the second derivative. If we wanted the third derivative, we would take it 3 times, but we're only going to talk about the second derivative in this class. Let's see, what else should we talk about? We have another definition here. It says the graph of f is concave upward on the interval a to b if f double prime of x is positive on that interval a to b. And the graph of f is concave downward on some interval ab if f double prime of x is negative on ab. So we have this concave upward and concave downward. So if your sine of f double prime of x is positive, that means the graph of f of x, notice we're talking about the original function. So here we're talking about how the sine of the second derivative tells us about what the original function looks like. So if our second derivative is positive, our original function is concave upward. And for this, I always think about the graph of x squared. Think about a parabola. That graph is always concave upward. But of course, I might not have the whole full shape of the parabola. I might just have half of it. So I might just have, say, the right half or the left half. I might have something that looks like either of these. I sort of think of these as sort of opening upwards. I've heard some teachers say it's concave up like a cup. So hey, we see that kind of cup shape, especially with the graph of x squared. It's just opening upwards. That kind of curvature is sort of opening upwards. Whereas if the sine of f double prime of x is negative, if my second derivative is negative, then that graph is concave down. I should say the graph of f of x of the original function. And you can, again, take all these examples now and just flip them upside down. So think about the graph of negative x squared, a parabola that opens downward, or I could have just half of my graph. So I might have, say, the right half or the left half, something like that. So I don't need the full parabola, but I should see that curvature, that graph kind of curving downward. I've heard concave down like a frown. If that helps you remember it, by all means, use that to help you remember which one is which. But this is kind of how we're going to determine where our graph is concave upward and concave downward. We're going to look at the second derivative, just like we did with the first derivative. So a lot of the methods you're going to see in this section should feel very, very familiar to what we did in 4.1. We're just extending them now to talk about the second derivative, and it tells us a new piece of information. So we're going to look at a couple of examples here. First up, determine the intervals where each graph is concave upward and concave downward. I have h of x equals x cubed. So if I want to determine where the graph is concave upward or concave downward, I'm trying to determine the concavity of the function. If I want to talk about concavity, I need the second derivative. So in this case, I need h double prime of x. So h prime of x, I need to find the first derivative first. My first derivative would be 3x squared. And once I have that, I'm going to take the derivative again. Second derivative, h double prime of x. Here I would end up with 6x. Just like we did with the first derivative then, we're going to act like we're finding critical points, only we're talking about the second derivative here. So these aren't critical points. Critical points only refer to the first derivative. These we might just call partition numbers here. They're numbers that break up the second derivative. I want to think about places where my second derivative is either 0 or places where my second derivative does not exist. I'm always kind of falling back on those two cases to help me partition up my number line. So first we'll consider, well, where is 6x equal to 0? We can divide both sides by 6. I end up with x equals 0. So that is a partition number of my second derivative. I'm going to care a whole lot about that number in just a second. H double prime of x does not exist. Again, I can look at the second derivative here. H double prime of x is equal to 6x. This guy here, h double prime of x, this is a polynomial. And I know that polynomials are continuous everywhere. So what that means is I'm really not going to have any new partition numbers. If you're considering this possibility, there really are no x values where h double prime of x exists. So you can kind of just say, you know what, there's not really any solutions to that possibility or to that equation. So I have my single partition number. I'm going to create a number line just like I did before, but now I'm going to create a number line for the second derivative. And here, hopefully, this is going to start to show why. Oops, not f double prime. We're talking about h double prime. I'm hoping that seeing this is going to make it clear that we should be labeling our number lines, because in this section, in the later sections, we're going to start to talk about both the first derivative and the second derivative, and I want to make sure that we're able to keep these two things straight. So make sure that you label your number lines. The only partition number we had on there was 0. And I'm going to, just like I did in the last section, I'm going to take a number on the left-hand side of 0, and I'm going to take a number on the right-hand side of 0, and I'm going to plug those into my second derivative, into h double prime of x equals 6x. So I'm going to start on the left-hand side. Let's say h double prime of -1. That's a number that's on the left-hand side of 0. So this is 6 times -1 gives me -6. And again, it's really the sign that I'm interested in. Here it's negative. So my second derivative is negative. I'll put some minus signs there. And then I know, okay, if the sign of f double prime of x is negative, my graph is concave downward. So oftentimes what I'll do is I'll just draw in the shape of a concave downward graph, and that's just to help me remember, oh yeah, it's concave downward over that section. I don't have to think about it quite so much later on. But I still need to take a number on the right-hand side of 0, so I'm going to take h double prime of +1. This is 6 times +1. This time I end up with a +6. So this time I have a +6, so my second derivative is positive on the right-hand side of 0. If the sign of f double prime of x is positive, we said our graph was concave upward. So I like to draw in that concave upward shape, kind of that classic y equals x squared parabola. And at this point, we've done most of the heavy lifting. Now we just need to interpret this number line that we've created, because I just need to determine, okay, where are the intervals where it's concave up, where are the intervals where it's concave down. Well, it's concave up on the right-hand side of 0, where the second derivative was positive. So if I want to talk about where this graph is concave up, it is concave up on this right-hand side of 0. So I'll say from 0 to positive infinity is concave up. And then what are the intervals that it's concave downward on? Well, it's concave downward wherever we had a negative second derivative, so on the left-hand side of 0. So it is concave down on negative infinity to 0. And that covers pretty much everything. That's all I'm really looking for. So hopefully this process, I think the actual mechanics and the process that we take through these problems, the steps that we follow, should feel very, very familiar to what we did in section 4.1. We're just working now with the second derivative instead of the first derivative. And then at the end of the day, we're talking about concavity versus where our function is increasing or decreasing here. So we're just gaining it. We're working with the second derivative and we're gaining a new piece of information. That's really all that changed. Let's look at one more example. Here I have f of x equals e to the negative x power. So again, I want to determine where is this function concave up, where is it concave down, and where, well, that's it. Just where is it concave up and where is it concave down. In order to determine the concavity, I need to find the second derivative. But if I want to find the second derivative, I need to start with the first derivative, f prime of x. Hopefully we look at this e to the negative x, and I'm looking at this power of negative x in particular. This is going to require a chain rule. And if you think back to the chain rule formula for e to the negative x, it says the derivative of the power, so I'll multiply by the derivative of negative x. That will be negative 1. Times e to the negative x power, or more simply just negative e to the negative x power. But this is just my first derivative. I need to take the derivative once more if I'm going to find the second derivative. So f double prime of x, now I'm looking at the derivative of this function right here. Again, I see exactly the same thing I'm going to run into last time. I have that power of negative x. Again, this is also going to be a chain rule. So our formula, our derivative formula for e to the u said, all right, we multiply by the derivative of that power. We multiply by our u prime. Derivative of negative x, that's going to be negative 1 once again, times negative e to the negative x power. That part stays the same. And then look at this, negative times a negative, I'm going to end up with a positive e to the negative x power. So here is my second derivative. And if you'll notice, hey, the second derivative actually the same as our original function. I think that's kind of fun, kind of neat. We have our second derivative. I want to think about places where our second derivative is equal to 0 and places where our second derivative does not exist, because those are going to create the partitions for my number line. Now, I have said this multiple times, I don't really like working with negative exponents. We don't have as much experience working with them algebraically, and so I think it's really easy to make a mistake. So what I'm going to do is I'm just going to rewrite this before I start to work with this. I'm going to rewrite this as 1 over e to the positive x power and just make that exponent positive. I think that's a lot easier for us to work with. Because now we say, okay, when the second derivative is equal to 0, you can do one of two things. You can take the whole function and set it equal to 0. 1 over e to the x is equal to 0. Okay, well, the first thing that we're going to do is we're going to multiply both sides by e to the x to get that out of the denominator. And that'll leave me with 1 equals 0 times anything is just 0. I could also have jumped straight to this, and I could have said, you know what, this function right here is only 0 if the numerator, if the top part of my fraction is 0. So I could have also just taken 1 right from the beginning and set it equal to 0. Now hopefully that equation that we ended up with here at the end raises some eyebrows, because 1 is not equal to 0. 1's a different number. So that means that this equation has no solutions. So okay, we don't have any partition numbers there, but maybe we do where the second derivative does not exist. For that, I'm going to look at the denominator, and again, I think this is another reason why rewriting this expression with a positive exponent is a little bit easier to work with, because I know that if I divide by 0, that expression is undefined. It does not exist. So I'm going to take my denominator, again, of e to the x, and set that equal to 0. E to the x is equal to 0. And I'm going to think about, well, how would I solve this equation? If I want to undo this, I would have to take the natural log of each side. But there's one problem. It's that this side over here, if you try to take the natural log of 0, if you type that in your graphing calculator will get all mad at you. It'll say error domain. It's because 0 is not in the domain of natural logarithm. So what that means for us is, once again, we end up with this situation where we have no solution. There's no x value that makes this equation true. So really, if I look at e to the x is equal to 0, there are just no solutions to that equation. So this is a really odd case. We've never really run into this problem before, but I think it's worth talking about. We actually don't have any partition numbers. Neither one of those cases gave us any x values to work with. But that's okay. I'm going to construct my number line just like I normally would. F double prime of x. What this means for me, normally if you think about what a partition number does, is it splits the number line up into two chunks. So you've got this interval on the left and this interval on the right. Well, we don't have that this time around. We just have the one big number line. We really have negative infinity to positive infinity. There's nothing to break up our number line. Which means I can actually take whatever number I want and plug it into the second derivative, plug that into f double prime of x. I can pick any number. And what that means for my result is that my function will either always be concave up or always be concave down, because my derivative, my second derivative, will either always be positive or always be negative. So I need to pick just any number between negative infinity to positive infinity. How about 0? I'm going to take 0, plug that into my second derivative. I'm just choosing 0 because I think it's easiest to work with. You can work with e to the negative x, or you can work with 1 over e to the x. I think that this positive exponent, I took the time to write it. Why not use it? So I'm going to use that positive exponent right there. But if you use the negative exponent expression, you'll end up with the same thing. This is 1 over e to the 0. I know that anything to the 0 power is 1, so this is 1 over 1, which is a positive 1. So, okay, what does that mean for us then? We have a positive 1, which means my second derivative is always positive. If my second derivative is always positive, then the graph of f is always concave up. So that means when it comes time to kind of interpret this number line that I've constructed, I will say that this function is concave up on the interval negative infinity to positive infinity. I also like to go out of my way just to let the reader know, hey, this is concave down nowhere. At no point is this graph concave downward. It is always concave upward. And actually, if you were to look at the graph of this function, you would see that it is concave upward always. What you would see if you graphed that is you have this sort of shape. This is a exponential decay function. You would see something that looks like this, where this opening, it's sort of opening upward right here, but it's always concave upward. So this is a really neat example. We won't see this happen all that often. We won't see this happen where we have our function either always concave up or always concave down. Most of the problems that we look at, most of the functions that we work with, there's some sort of shift in concavity because that makes our problems a little bit more interesting to work with. But just in case we don't, this is a really nice example to look at because if you don't have any partition numbers, your graph is either always concave up or always concave down.